Okay. So today I want to talk about duality, about linear programming with you guys. Actually, how to say? I know that you will have exam on Friday, right? Friday. But at first I was wondering whether Dr. Costello will ask me to talk about, to hold a review session for you. But it turns out that she wants me to cover something about duality. So let's just get started. So duality, at first I want to just write down the form to you. So duality, from this name, you know that it is dual. So dual means that we have something called primal problem and also a dual problem. Primal problem and dual problem. So in today's section, we want to do the primal problem in this form, which is we want to maximize Z, which is C transpose times X. And the constraints AX less than or equal to B with X non-negative. This is the form of our primal problems that we want to discuss today. And the dual problem, I first write it down. It is called minimize V equals to B transpose Y, such that A transpose Y greater than or equal to C and Y greater than or equal to 0. Okay, so first write it down here, and I will give you an example to illustrate what it means. So let's consider this example. So suppose we have a manufacturer, whatever the name. So this manufacturer uses 3 kinds of resources, say A, B, and C. And they want to manufacture 3 kinds of products, which is D, E, and F. And in this table, the number is just, let me first write down the numbers, 8, 6, 1. So you can just copy this example. This example was given by Dr. Costello. So each number in this table means that how many units of A, B, C does it need to produce 1 unit of product? Say with to produce 1 unit of product D, you need 8 units of A, 4 units of B, and 2 units of C. Just in this manner. Okay, so what we also have is currently we have 48 units of A, 20 units of B, and 8 units of C. And as for the price, 1 unit of D is 60, and 1 unit of E is 30, and 1 unit of F is 20. Okay, so this is our problem. Let me repeat it. So suppose you are a manufacturer. You have 3 kinds of resources, A, B, C. You want to produce the products D, E, F, and this table means how much resource do you need to produce 1 unit of D or E or F. And you have these many units of A, B, C, these resources. And for the price of the products, they are shown here. So what we want to optimize is, suppose you are the manufacturer, you want to maximize your profit, right? Do you think they are too noisy? You're fine, okay. So when we talk about the duality in this problem, I want to claim that in the primal problem, we want to from seller side. From seller side means that suppose you are the manufacturer, you want to produce these products and you sell them out, so you are the seller. The primal problem when you construct the primal problem, you are thinking from the seller side, and you want to maximize the profit. And also there's a dual problem, which is equivalent, but it is from buyer's side. From the buyer's side. And so what would we minimize if we are thinking from the buyer's side? Say suppose I am the buyer of these products, DEF. What do I want to minimize?
Minimize the cost.
The cost, right? So that's to say minimize the payment, or say the cost that I pay to this manufacturer, right? Okay, so these are two ways of thinking, but actually they are equivalent from the seller side or from the buyer side. So how do we construct our primal problem? So primal, suppose we want to maximize the seller's profit. So we can just design our decision variables as x1 means number of D to produce, and x2 means the number of E to produce, and x3 means the number of F to produce. These are my decision variables if I want to think from the seller side and I want to maximize the profit. So can you tell me what is my objective function now? I want to maximize my profit. What is my profit?
Price times.
Yeah, right. So this is very easy. I want to maximize 60x1 plus 30x2 plus what else? 20x3. And the constraints are just that the number of the amount of resources that I have used to produce this many DEF products do not exceed the limitation of the units of ABC, right? So it is just 8x1 plus 6x2 plus x3 less than or equal to 48, and 4x1 plus 2x2 plus 1.5x3 less than or equal to 20, and 2x1 plus 1.5x2 plus 0.5x3. This is less than or equal to 8, and x1 to x3. They're all non-negative. Very easy, right? So this is the primal problem, which is what we usually consider. But now I want you to think of the dual problem from the buyer side. You want to minimize your payment. So how can you design your decision variables if you want to think from the buyer side? This I have to claim that this part is a little bit tricky because when we consider the economic interpretation of the dual problem, sometimes it is not that straightforward to consider compared with the primal problem. So actually, what we do is like this. So in the dual problem, we design Y1 to be the price paid per unit of A. I think that this is a little bit weird, but actually this is just an economic interpretation when we design the dual problem. So because you are the buyer, so you buy DEF. So Y1 means that because you know that in order to manufacture the DEFs, you need to use the resources ABC. So Y1 here, we want to define it to be the price paid per unit of A, and Y2, the price per unit of B, and Y3, the price you pay per unit of C. So as I said, you want to minimize your payment. So that's to say, you pay Y1 per unit of A. So
48 Y1.
yeah, 48 Y1 plus 20 Y2 plus 8 Y3, right? Such that what are the constraints? The constraints, so I would like to interpret the constraints in this way. So I am the buyer and say, you are the seller. So you will not sell unless I pay at least as much as you want, right? Think about this. You want to sell for 60, 30, and 20. These are your baselines. You cannot. So you want to sell as long as I give you what I actually pay you is at least 60, 30, 20 for each of D, E, F. So constraints are just that 8y1 plus 4y2 plus 2y3 greater than or equal to 60. This is for product B, and 6y1 plus 2y2 plus 1.5y3 is a 30, and y1 plus
is 4y1.
Yeah.
Yeah, 4y1 for the second assumption.
Are you sure? So
yeah.
Product.
Oh, sorry, it's my bad.
Yeah.
It's my bad.
So you need 6 units of A, right?
Yeah.
So y1 plus 1.5 y2 plus 1/2 y3. This is at least what? At least 20. And of course, you should have y1, y2, y3 no less than 0. Right. So this is the dual problem. You can just copy this problem first, and then I will talk about the theory behind the duality. That's to say, to help you to understand why duality really works, which I think is much more important. And actually, duality is is a very important topic in optimization. I will spend most of the time today to talk about the theory behind duality. And actually, Dr. Costello also asked me to cover an application of duality theory, which is the minimum node cover. Has anybody heard of this problem? Minimum node cover. Okay. I will talk about it later, but that is, I will just spend a little time on it, because once you know the theory behind duality, you should be able to deal with any applications that you want. Okay. So now let's talk about the theory. Okay, so let me write it again. Duality theory. You want to maximize C transpose X such that AX less than or equal to B with X non-zero. You have already copied this, so I'm just rewriting it so that we can look at it and discuss. A transpose Y greater than or equal to C, Y greater than or equal to 0. Okay, so what we observed from the example that I've given you is that, so in the primal, this is the primal problem, this is the dual problem. So actually in the primal problem, a decision variable in the primal problem, when you switch to the dual problem, it corresponds to a constraint. Just like the examples that I have just given you, in the primal problem, what is your decision variable? The amount of in the primal problem, the decision variable is about the products D, E, F, right? And then in the dual problem, it becomes a constraint. Because remember that here I told you that you want to sell me as long as my payment for this product is greater than or equal to the price that you want. So in the primal problem, a decision variable changes to a constraint when you switch to the dual problem. And correspondingly, a constraint in the primal problem, it corresponds to a decision variable. So actually, when you are doing your homework, let's just brainstorm what you did in your homework. So in your homework, there were some problems in which you are required to from a linear programming, right? So as I have told you in thinking week 2 or so, when you are constructing a linear programming for a network problem, basically you have 2 ways to do it. The first way is that you set the decision variable with respect to the nodes, and then you construct the constraints about the arcs, right? Or you can do it in the opposite way. You set the decision variable with respect to the arc, and the constraint is about the node. So these are 2 ways which are equivalent actually. So this is the basic stuff. And the first series that we want to introduce is weak duality theorem. So weak duality theorem is something like this. So suppose X is a feasible solution to primal. So I will write SOL to be the solution. Okay. So suppose X is a feasible solution to our primal problem, which is stated here, and Y is a feasible solution to dual problem. What do we have? Then C transpose X must be less than or equal to B transpose Y. So look at what it means. X is a feasible solution to the prime. That's just AX less than or equal to B, and X is non-negative. And Y is a feasible solution to the dual, means that A transpose Y is greater than or equal to C, and Y is also non-negative. Then we can claim that C transpose X, which is the objective function in the primal, is no more than B transpose Y, which is the objective function in the dual problem Y. This is a very, very simple proof. So the proof is like, so we know that AX less than or equal to B because of the feasibility of X. And Y transpose A, this is greater than or equal to C transpose. So you will see that now I have taken the transpose on both sides of this constraint. As Y transpose A is greater than or equal to C transpose, that's from this constraint. Okay, and also we have X and Y to be non-negative. Then what do we do here is that let's consider this guy. Y transpose AX. So from this AX less than or equal to B, if we multiply Y transpose on both sides, we know that Y is non-negative. So we must have Y transpose AX is less than or equal to Y transpose B. Is that correct? And also, if we think of it in this Y transpose AX in this way, we multiply X to Y transpose A, then it must be greater than or equal to C transpose X, right? Because X is non-negative. So that's to say, this inequality leads to this one, and this inequality leads to this one. And also, these are both based on X and Y to be non-negative. So this is our result. So C transpose X less than or equal to Y transpose B, which is, and Y transpose B and C transpose X, we know that both of them are scalars. So it is equivalent to B less than or equal to B transpose Y. Then a very natural question is, what the hell do we need this? Why do we need this result? What does this tell you? So think about this. So suppose, let me just sketch a graph. We have C transpose X less than or equal to Y transpose B, and we know that X is any feasible solution to the primal. Y is any feasible solution to the dual. So what we can sketch is that this is the dual, this is the primal. And the value of here I mean the objective function. And what can we say is that the value of the objective function in the primal is always less than or equal to the objective function of the dual problem, right? Just as this graph has suggested. So that's to say, the feasible solution of the dual problem sets an upper bound to the primal. Is that correct? This is an upper bound to the value of the primal. Okay. Then here I want to say, so this leads to the something called certificate of optimality. By the way, for this terminology, certificate of optimality, I refer to some online resources because actually the resources provided by Dr. Costello is not concrete enough, so I refer to some other resources. For this terminology, I just referred it online. Okay, so it is called certificate of optimality. What does it mean? It means that so if x, y are feasible solutions to primal and dual. So P means primal, D means dual. I just write it for simplicity. X is the feasible solution to the primal, and Y is a feasible solution to the dual. And suppose further we have C transpose X is equal to B transpose Y. Then what can we say? Then we can say that X, Y are both optimal solutions to P and D, respectively. So think about this. As I have introduced here, so suppose X and Y are both feasible solutions, to the primal and dual, respectively. And what we can conclude from the weak duality theorem is that C transpose X must be less than or equal to B transpose Y. Now, suppose C transpose X is equal to B transpose Y. Then we can say that X and Y are both optimal solutions to the primal and dual, respectively. Is that easy to understand? Okay, I see Thomas nodded his head. So how about YouTube? You don't understand? Okay, so let me just quickly illustrate what does it mean. So that's to say, so we say that for any Y, which is feasible to the dual problem, we have B transpose Y is greater than or equal to C transpose X, and also for any X. So now we have some, suppose we have Y0 and X0 such that B transpose Y0 is equal to C transpose X0. Then what can we say? Then, because X0 is also a feasible solution to the primal problem, right? This is so C transpose X0. This must be less than or equal to B transpose Y. This is for any Y, right? X0 is a feasible solution. And because of the weak duality theorem, so we can say that for any Y, it is less than or equal to B transpose Y. Is that correct? And also, it is also so for B transpose, oh, sorry, this arrow should be here. And for B transpose Y0, this should be greater than or equal to C transpose X for any X, right? So that's to say C transpose X0 is greater than or equal to C transpose X for any X. X0 should be an optimal solution, right? And also for Y0, Y0 should also be an optimal solution. X0 is the optimal solution to the primal, and Y0 is the optimal solution to the dual. So this is called the certificate of optimality. That's as long as you can find X and Y, so that B transpose Y is equal to C transpose X, then you can just conclude that they are both optimal solutions to the primal and dual. Okay. Okay. Then I want to say infiniteness and feasibility in duality. This is also some theorem. So it is stated in this way. So if the optimal solution in primal is positive infinity, then by weak duality theorem, no feasible solution to dual. Think about this. Sean, can you tell me why?
I don't know really the question.
Just read it. Okay, let's read together. If the optimal solution in the primal problem is positive infinity, that's to say it is not bounded from above, then by the weak duality theorem, no feasible solution to the dual.
Yes, that's correct.
Okay. I just need to make sure that you guys understand. Okay, so no feasible solution to the dual problem. Okay, so then correspondingly, if the optimal solution to dual is minus infinity, then no feasible solution to primal. So these are singular, because we know that the dual is an upper bound for the primal. So if the optimal solution to the dual is not bounded from below, then of course no feasible solution to the primal. Okay. What else? Oh, by the way, I need to say that the certificate of optimality, this does not imply that there exist feasible solutions x, y, such that C transpose x equals to B transpose y. So the certificate of optimality only tells you that if you can find x and y that satisfies this requirement, you can conclude that they are both optimal solutions to the primal and dual. But this does not imply that in any problem there must exist some feasible solution x, y, z satisfies this requirement. Okay. So this leads to our next theorem called strong duality. So remember that we have already talked about weak duality. So now, well, we can say something about strong duality. The strong duality is stated in this way. The dual has an optimal solution if and only if the primal has to say, or say that our primal problem has an optimal solution, even only if the dual has an optimal solution. So they happen simultaneously. And then if x star and y star are optimal solution to primal and dual, C transpose x star is equal to B transpose y star. Yeah, so remember that in the certificate of optimality, we say that if x and y are feasible solutions and they satisfy C transpose x equals to B transpose y, then we can say that they are optimal solutions to primal and dual respectively. But here in the strong duality, we say the converse way. If X star and Y star are optimal solutions to the primal and dual, then we can say that C transpose X star is equal to B transpose Y star. So this is in the converse way, right? But here I will not prove the strong duality, because strong duality, if you want to prove, you need to use something called KKT condition and Farkas lemma. Yeah, so if you want to prove it, proved by KKT condition is a very famous condition in constrained optimization. It is called Crush-Kuhn-Tucker condition. So KKT means three guys' names. Crush-Kuhn-Tucker condition. And also, if you want to prove it, you need to use Crush-Kuhn-Tucker condition and also Farkas lemma. So I will not sketch the proof here, but just to remember it, this is about the strong duality. And what else? Next, I think you should also be able to see this in the lecture. It is called complementary slackness. Has Dr. Costello talked about this concept in her lecture? Thomas, do you remember?
I think she mentioned it. I don't remember if she went over it.
Okay, she might mention it. Okay. So complementary slackness. So that's just a review what the hell it is talking about. So complementary slackness means that so X, Y are feasible solution to primal and dual. This this sentence we repeat a lot in today's section. X and Y are feasible solutions to primal and dual problems. And we can also say that X, Y are optimal solutions if and only if. Yeah, this is a sufficient and necessary condition. If and only if what? If and only if B minus AX transpose Y is equal to 0. And A transpose Y minus C transpose X is equal to 0. This might seem a little bit weird at first. So in order to let you guys think about it, I will copy the primal and dual here. So the primal is maximize C transpose X with AX no more than BX non-negative, and the dual is to minimize B transpose Y such that A transpose Y is greater than C with Y being non-negative. So first, I give you several seconds to look at it, just to compare. So you see that here are B minus AX transpose Y. That's B transpose Y. What is B transpose Y? B transpose Y is this guy. And AX transpose Y. That is X transpose A transpose Y. So what does it mean? It means that you multiply X on this side. Okay. And for A transpose Y minus CX, so you just look at the primal problem and you see what it is. This is called complementary slackness. Basically, why do we need it? This is a very good question. When I studied complementary slackness, I just didn't understand why do we need it. So, but yesterday when I prepared for today's section, I think I figured out the answer. Why do we need it? Suppose, I will not write down, but I will just speak. Okay, why do we need it? So complementary slackness, look at the statement. What does it tell us? X and Y are optimal solutions to the primal and dual if and only if these two equations hold, right? So the reason why we need it is that, so suppose we know any one of X, say we know X, then does it mean that we can solve for y? We can figure out what y is just based on these two equations. And suppose we know y, we can also figure out what x is, right? Because in these two, look, these two seems just like two equations, but actually these two are systems of linear equations. You have many equations, and if you know x, you can solve for y. If you know y, you can solve for x. So I think the most important thing, the reason why we need duality is that sometimes for some linear program, if you transform it to the dual problem, it is easier to solve. And suppose you can solve the dual problem easier than the primal problem. Here, I mean, easier means that the time complexity, it costs less complexity to solve the dual problem, and you obtain y. Then you can just use complementary slackness to transform to x. I think this is the main reason why we need duality and complementary slackness. And the weak duality theory, strong duality theory helps us to make sure that the optimal solutions must occur simultaneously. As to say, this is so this is the dual, this is the primal. Actually, right? They achieve the minimum and maximum simultaneously. This is what the strong duality and weak duality theory tell us. They tell us that the optimal solutions should occur simultaneously. Okay, then let me prove this complementary slackness theorem. So remember that here we are proving something called if and only if. So we need to prove two parts. First, this is the only if part, right? So we know that x and y, since x, y are feasible solutions, then from feasibility, we can say that okay, ax is less than or equal to b in b, and aty is greater than or equal to c, and x, y are both non-negative. These are the feasibility. This is what the feasibility tells us. So if x, y are optimal, then look at this thing. If we write A transpose y minus C transpose x plus B transpose B minus AX transpose y. So what is it? What is this? If we just open the bracket, what we get is y transpose AX minus C transpose x plus what? B transpose y minus x transpose A transpose y, right? So we see that these two guys cancel each other, and we have B transpose y minus C transpose x. So this equals to 0. This is by strong duality. This guy goes to 0 because of the strong duality, which is stated here. So we have this equals to 0. So we can say that B minus AX transpose y, this is equal to A transpose y minus C transpose x equals to 0. Why? I have a question to you. Why? So we see that if you add them up, you get 0. Why can we say that these guys are both 0? Yeah, here's my question to you. Why? So the reason is that non-negativity. So you see that A transpose Y is greater than or equal to C, right? So A transpose Y minus C, this vector, in this vector, A transpose Y minus C, every element is greater than or equal to 0. Is that correct? Yeah, this guy is greater than or equal to 0. And this guy, X, is also greater than or equal to 0. So their inner product is also greater than or equal to 0. And the same for this guy, greater than or equal to 0, greater than or equal to 0. So their product is also greater than or equal to 0. Two numbers which are both non-negative add up to 0, then what can we say? That was 0. Right? Clear? Okay, very clear. Okay, and the converse direction is easier. So what is the converse direction? So we know that the two equalities, then we can say that 0 equals to ATY minus CTX plus B minus AX transpose Y. So we can refer to this. If we add them up, what we get is BTY minus C, what is this? Minus CTX. If you add them up, you get BTY minus CTX. This is equal to 0. Then, so we have BTY equals to CTX. So we can say that X, Y are optimal. Why? Based on what we have talked before. We have these two equalities. Then if we add them up, we get 0, and we get B transpose Y minus C transpose X equals to 0. So B transpose Y equals to C transpose X. That's to say, the objective function of the dual is equal to the objective function of the primal. So by the certificate of optimality that I have introduced before, X and Y are optimal, right? So this is the proof for complementary slackness. The main idea is that if you use complementary slackness, as long as you have the solution for the dual, then you can just derive, you can just calculate the solution to the primal easily by these two equations. So these are for complementary slackness. And I see that we, because we started at 10:35, so we still have 7 minutes left. So I will just briefly introduce the application. The application is called node cover. Let's return to the network. Okay. So suppose we have G and A. This is a network. And undirected. So what is a node cover? So a subset, let's say N1, which is a subset of N, is a node cover. If each arc in A has at least one endpoint. So think about this. A node cover means that this is your graph. This is your graph G. And a node cover means that it is a subset of the nodes. And every arc in this graph has at least one endpoint in N1. So the most trivial way is that N1 equals to N. Then this is definitely a node cover because every arc has at least one endpoint in the in this N1. Then there exists a problem which is called minimum node cover. So minimum node cover means that how can you find a node cover such that it has the minimum cardinality? For example, in this problem, so a minimum node cover can just be these two, right? Then only two elements, and every arc has at least one endpoint in this N1. So how can we formulate this minimum node cover problem? So min node cover. So we can just let xv. This is to be 0 or 1 to so xv, v means something in a node set. That's to say for every node, you have two options: to include it in a node cover or not include it in a node cover, right? So xv to describe whether v is in the node cover or not. So this is a binary variable. And then the model becomes, we want to minimize in the node set xv such that xu plus xv is greater than or equal to 1 for any uv in A. And also xv is in 0, 1. Is that clear? Well, let's see. Xv can either be 0 or 1. That's to say you can either you have two options. V, you choose it or not choose it. And you need to make sure that for every arc, at least one endpoint is in this node cover. And what you want to minimize is, you want to minimize the number of points in this node cover. Yeah, this is the minimum node cover problem. And yeah, I see that we have run out of time. So I will talk about some, now I want to talk about some very important points. So yesterday in my office hour, one student asked me about why do we need totally unimodular matrices? Yeah, I think you have already heard of this terminology, totally unimodular matrices, right? So actually, when I learned this course, I also find that it is kind of confusing. So I looked up something on some online resources. So a totally unimodular matrix, what we usually do is use this to describe a node arc incidence matrix. Say AX less than equal to B, and our X is with respect to the arc, and A is the node arc incidence matrix. So suppose A is if A is TUM and B is integral. Then with the help of TUM, we can say that so suppose we are maximizing or minimizing C transpose X. If A is TUM and B is integral, then the optimal solution to any C transpose X must be an integer point. So you see that in some problems like this, you need to make sure that your solution must be integers. However, you may also have heard of a terminology called LP relaxation. That's to say, initially you just want it to be 0 or 1, but you can just write it to be xv less than or equal to 1, greater than or equal to 0. Now you have transformed an integer programming to a continuous programming problem, which is much easier to solve. So if you have the condition of totally unimodular, then you can just feel free to do LP relaxation and solve for it. And TUM guarantees that what you finally obtain must be an integer point. So in this way, you don't need to solve for an integer program. So I think this is the main reason why we need the concept of totally unimodular. This concept is widely used in integer programming, but integer programming is not the concentration of this course. It is concentration of convex optimization. It is called EN.553.463, taught by Amitabh Basu. So if you have interest, feel free to take that course. Okay, so this is I think that's all for today's section. So I think we can end here. And I think Dr. Castello should have already uploaded the notes for node covers, edge covers, independent sets, and matches. So please read them by yourself, because I have already introduced quite a few theories about duality. So if you understand the theory of duality deeply, you should be able to understand something, node covers, edge covers, independent sets, matches easily, because they are dual to each other. Okay, so I think that's the end of today. Thank you.